to talking about hearing. Let me go ahead and get those captions going. We're gonna. Yeah.
Do you have PowerPoints posted?
Yes, I should. Do I not? I thought I uploaded them yesterday. Let me take a look.
I don't see.
Okay. How about I upload those right now?
Sorry, I was just like,
No, what ended up happening, I wanted to make sure that the links were current and I forgot to upload them. So let me go ahead and do that right now so you can see what I see. And it's okay. I'm sorry I didn't get that. Welcome back from spring break. That's really distracting.
Yeah.
All right. Well, I have to upload the slides, so you have like maybe 2 more minutes to play around with it. Sorry about that. I had the slides ready to go. I thought I uploaded them. I'm so sorry, y'all. And to be fair, y'all could have gotten by with 1 day without them, but I know you like having them. Wow. Ouch. I never like that. I don't like seeing anybody cry.
If you cry, I will leave you.
Now it's being pokey. Give me just a minute. Oh my gosh, hurry up.
Andy's dad has been able to think so. So we're going to hospital. So I can also buy a dog.
Okay, let me see if it was put up or not. I'm kind of, it didn't. That's so rude. Okay. It was like you hit the back button twice. I don't like it. Well, you know, folks, every now and then it's a good day for Murphy's Law. Apparently this is it. Thanks for throwing me off my game, Natasha. It's okay. I'm not kidding. Like, I'm kidding. For a minute, I was like, I'm not kidding. No, I'm kidding.
Like the PowerPoints, that's where I do my notes.
Well, Edge is so slow. Okay. Okay, it did it. Did it? Did it do it? Yes. Okay. So it's going to be in higher order vision, even though technically it's part of the 3rd unit. So just be prepared for that. All right. So let's get back to where we were. You should have everything that I have right now. So let me go ahead and go into a duplicate slideshow. So we are talking about motion perception. Ooh, we actually have some motion here. All right. So we're going to talk about a few different things in this unit. So we're going to talk about how the brain handles motion perception. We're going to talk about how we actually interpret different types of moving stimuli. We're going to talk about eye movements and saccades. So we're going to do some demonstrations where you are going to have to look at other people's eyeballs moving around. You are also going to have to look at your own eyeballs in a mirror or in your phone. Then we're going to talk about the development of motion perception. It turns out that with motion perception, things do not necessarily smoothly progress. There are critical periods for different types of motion perception. So we're going to start by talking about how the brain actually handles the different types of motion. So to understand motion, it's very clear that that motion is an interesting thing to kind of talk about. So motion, really, when it comes down to it, is keeping track of something's positional change over time. That's all that motion is. It's a change in position over time. But here's the problem. So let's say, for example, that I have 2 different areas of space. So maybe Lauren moves from this seat over to the other seat. So I have her tracked in 2 different places. Now, right now, Natasha's sitting in that spot, so I've also got activity in both of those spaces. Why don't I interpret that as motion? So it's kind of clear that we need to make a distinction between one object changing position over time and something like two separate objects that are occupying adjacent areas of space. So researchers have tried to kind of come up with what they call a theoretical motion detector. And so what sort of things are you going to need to detect visual motion? So first of all, we know that there has to be a change in position over time. Additionally, we're watching change over time, which means we are constantly looking at adjacent positions in space. I don't suddenly jump from this side of the room all the way to this side of the room. It is a very smooth motion where I am constantly moving through adjacent visual spaces. So we need to have two different adjacent visual receptors that are tracking that change. You also need to be able to incorporate a time delay. So we need to be able to track a delay in terms of time. Now, can anybody tell me why we would theoretically need to track delay periods? Why would we need to look at a delay when we're talking about motion? Yes, Sarah. Right. So it's not like as I'm moving, I'm suddenly going to be over here. I'm going to be over here, and after a delay, I will be over here. After another delay, I will be over here. It's not instantaneous transmission. So here's an example of what this looks like. And folks, this is probably the most difficult thing that we're going to talk about today. This is it. Don't pull that face. I promise you it's not that bad. And I'm kind of talking you through it here. So let's say, kind of. Okay. So here we're looking at a ladybug, and you could just imagine a ladybug just walking on the table, walking on your hand, walking on my dog. He has ticks crawling on him all the time and he never notices. To be fair, he has a flea collar. So usually the ticks will jump onto something else, like other people. Ew. Okay. So let's say that we're looking at a ladybug. He'll stop that. Like that. So let's say that we're looking at a ladybug kind of walking across space. So here are our receptive fields. So notice that as the ladybug moves through space, adjacent visual receptive fields are going to keep track of that. And each of these receptive fields is basically under the purview of neuron A and neuron B. And I think in your textbook, it's neuron 1 and neuron 2, but here we have A and B. So A and B are basically separate neurons. So as the ladybug moves from one receptive field to the other, we have our motion detection cell. Notice that it happens with A, and then after a slight delay, that message is being sent from B. So basically, our motion detection cell will connect to both of these neurons with adjacent overlapping receptive fields to basically detect different differences in position. So you can kind of see here where this might be a problem, right? So here, there's a little bit of a delay, but part of the problem is we need to have a delay component here. And here's why. As it stands right now, if we only have a motion detection cell without taking into account that delay component, I could have a ladybug in this receptive field, a different ladybug in this receptive field, and my motion detector would go, oh, it moved. Because there's no delay, and because there's no delay, it could potentially interpret two separate things as occupying motion. And we know that that's not how motion really works. Motion is basically a change in one object's position across multiple receptive fields. So a theoretical motion detector needs to include this delay component here marked D. And this delays transmission of input from A to account for that time delay. And then additionally, if we want to get even more technical, we can include something like X, which is a multiplication factor. Basically, this is designed to only fire when we have D and B active. So that way, this can potentially account for the same object moving and changing positions over time. But because this is based on a delay component, what we're going to see is that if I have one ladybug here and a completely different ladybug here, that will not lead to a time delay. And as a result, motion will not be detected because of the multiplication factor. The multiplication factor only comes into play when there's been a positional change and there's been a time delay. That is the most technical that we will get in this section. Okay. So you can kind of see how this would work over two small receptive fields. Here's what this would look like over a larger period of space. So theoretically, we could take all of these different overlapping adjacent receptive fields, and we could make this happen over a larger area. And this potential motion detector can explain things like apparent motion. So I haven't shown you all of the pictures here, but here we have some still images of Daffy Duck trying to do a dance. And you can kind of see that based on the still images, if you cycle through these frames, even though each of these is a still image, when we put them together very close in time, we will get the appearance of motion. This is also very similar to things like flip books. How many of you have looked at a flip book before? Or how many of you have ever made a flip book before? So the basic idea of a flip book is you use still images flipped very closely in time to create the sense of motion. And we do actually find that motion can be detected in the absence of actual motion. So this is why I was kind of logging on. You should all be able to see this. Oh, really? Okay. All right. What do we want? Come on. I thought I had logged on to the thing. Oh, I've already done it. Oh, never mind. I'm already there. So we are going to talk a little bit about apparent motion. So what we are kind of looking at here, I'm going to go ahead and hide these floating controls. So here we're going to look at apparent motion. And basically what will happen is I'm going to show you two purple circles that are going to flash on and off. And basically, with a long enough delay, what you should perceive is that the circle moves back and forth. And this is what is known as apparent motion. So I'm going to go ahead and zoom in on this a little bit so that you can see. So we're only going to do a delay of 100. So go ahead and take a look at this, and this will be recorded for you, so you should be able to see it. It kind of looks like it's moving back and forth. Yes? Now, notice that that's not what's actually happening. So if I slow this down a little bit, if I make the delay a little larger, does it still look like it's moving? A little bit, yeah? Kind of? Okay, now let's go ahead and take that to maybe, let's take it all the way to the end. This is 500. So this is basically half a second between them. Okay. Do you still perceive motion there? Okay, cool. So now here's the thing that's really critical. You realize that they're two different circles, right? They actually are. There's not a positional change, but because the time interval between them is so short, your brain perceives a change in position and in motion when none has actually happened. So the experience of apparent motion, as you can kind of see here, it's dependent on how separated the two stimuli are from each other and the alternation rate. So here's something that we can do. We can actually move the circles around a little bit. So now, watch this. Do they still look like they're moving a little bit? I'm getting a little bit of motion from there. but it's really just two separate circles appearing at different points. So the farther apart that these are, the less likely that you are to perceive that smooth motion. I'm going to drag them all the way out and see if you can tell a difference there. Now it just looks like two different circles popping up. Is this kind of making you sick, Natasha?
Yeah.
Okay. Now, if we move those closer together to the point where they're right on top, like where they're like this, where they only overlap this much, that looks more like motion, right? So it's clear that apparent motion, they have to be really close to each other in space, or else we won't perceive it. Additionally, the time delay needs to be really short as well. Now, another thing that we can do, we're going to do this. I'm going to put this at the shortest delay. And I was going to say, we're going to do a delay of 10 milliseconds. That's it. Now, I'm going to do this. If you don't want to look at this very long, it might be a little unsettling. Are you ready? Okay. Ugh, you don't like that, do you? Now, in this case, does it look like it's moving? Not really. It looks like it looks like it's kind of flickering a little bit. This is what is known as phi or phi motion. This is a perception of motion without immediate positions. So it may look like a single circle that kind of jumps back and forth. So this is what's called apparent motion. We're going to come back to this particular set of exercises. We're going to spend a lot of time on that web page for some different examples. So apparent motion results from so two things that you need for apparent motion. First of all, you need those to be really close together in space, and the time interval between each of those still frames should be very short. So this results from the rapid alternation of objects that appear in different locations in rapid fire succession. So one of the things that we find is that a lot of the problems that we talked about previously are still going to be an issue when we talk about motion detection. Now, this was a question that was asked on your previous exam. We talked a little bit about the correspondence problem. And just in case you needed a reminder about the correspondence problem, this comes back from our discussion of binocular disparity. Each of our eyes gets a slightly different view of the world. So when we are viewing an image, we need to figure out what part of the image corresponds to each eye's image. And it turns out that the correspondence problem remains an issue when we talk about motion detection, because motion detection involves a change in frames. So in the case of motion, if I see motion between frame 1 and frame 2, what feature in frame 2, this change over time, corresponds to what we see in the original frame? Next, we're going to talk about something that we haven't talked about before, called the aperture problem. And basically, the aperture problem works this way. So another word for an aperture is a hole. So if we are viewing motion through some type of opening or some type of aperture, one of the things that we're going to find is that the local area of motion is actually going to be ambiguous. So there's a difference between motion of local features and motion of global features. And we'll talk a little bit more about how the aperture problem works on the next couple of slides and with the next few demonstrations. Okay. So I will let you go ahead and write this down. Okay. So, oh, it cut off my font. I hate that. It didn't even like my font. So the correspondence problem kind of works like this. So let's say that we're watching we're watching a square, and as you can kind of see in the top left corner, the arrow is moving in a downward diagonal motion. So basically here, between frame 1 and frame 2, the square is going to move down and to the right. Now, here's the thing. If we are viewing this particular portion of the square, these 3 circles part of the square, and we see them move this way, we have an issue with correspondence. It's possible that they could have moved straight down, or they could have moved down and to the right. So we're going to do an example of the correspondence problem, once again, kind of going to this section. So right now, here's movie number 1. So you can kind of see this is an instance where you can see with no aperture, you can see that the square is moving back and forth on that diagonal. Now, let's say that we look at those 3 circles that I mentioned, but we're viewing them through an aperture. Now, can you tell me which way those three components appear to be moving? Point to the direction in which they're moving with your hands. Up and down? They look like they're up and down. Now, if we remove this aperture, that's not what's happening overall. But when we view something through an aperture, we are not sure which way the motion is actually operating. So the direction shifts to up and down. And one of the things that you'll notice is that it also kind of looks like the speed of motion has slowed down a little bit, hasn't it? So here again, here's without the aperture. It looks like it's pretty quick. Here's with an aperture. Now, let's say that we add additional apertures. Watch what happens. Now, the motion becomes a lot more clear, and we go back to that diagonal motion. And that's because in this case, you can actually integrate these sources into a unified square. Now, is everybody perceiving that original motion? You might actually be perceiving 2 different rectangles, one moving across from left to right, and one that's moving up and down. Is anybody getting that? It just happened to me. You can kind of shift between that diagonal motion and then the up and down, left and right motion. So, where did you go? So here's kind of the aperture problem, and it's related to correspondence. So with the aperture problem, basically, we can't necessarily tell the overall direction of motion when something is viewed through an aperture. So here we have a few different cases. So here, this particular piece of striped material is being moved up and to the left, but that's not necessarily what you will perceive in this aperture. Likewise, if we move this up, what you're going to perceive is that it's kind of moving downward, despite the fact that that does not match the global motion. And then finally, we have moving to the left, but you might actually perceive this as going down and to the right. So again, we can't always tell the overall direction of motion when we are viewing something through that aperture. So again, going back one more time. So here's another version of that aperture problem. So here are those 3 different ones that I mentioned. Now, can somebody tell me in what direction they're all moving? What direction are they all moving? They all kind of look like they're moving upward and to the left, yeah? Y'all gave me a cold. And I'm finally over it, but now I've got this terrible cough that will never go away. So in this case, they all appear to be moving up and to the left, but now let's take a look at the true motion of each of them. One is moving up and to the right, or up and to the left, which is the true motion. One is moving up and one is moving left. So we can't necessarily tell the overall direction of motion when we're viewing local motion through an aperture, and we don't have the entire context. Without the global direction of motion, all of these look like they are going to be moving in the same direction, and it turns out that that is not actually the case. So, a little bit more of an explanation of this. When the three rectangles are visible, their edges provide unambiguous motion cues that help your visual system interpret the true motion of stripes. Without the global motion cues, your system is going to find the simplest explanation of the local motion of the stripes. They are moving up and to the left. So when we don't have a sufficient amount of global context, we are going to default to the simplest explanation, the motion of our local features. But remember that judging local features does not necessarily mean that that's what's going on with the global motion. So how is the direction of motion computed? So like I said, the more apertures that you have, the more openings that you have, that's more context that you have. So several apertures or several receptive fields can provide additional information about overall global motion. And there are several possible directions of motion per aperture that are compatible with a stimulus. And generally what we're going to find is that we are going to vote on the basis of consensus. So basically all of the apertures have a certain direction of motion, and basically the ones that all match will determine the global motion direction of the object. So here's what I mean by that. So let's say that we're looking at our square that moves down and to the right, down and to the right, back and forth, back and forth. So the blue square is frame 1, the green square is frame 2. So here we've got our 4 different apertures. Now, if we only had one of these apertures, there are several different directions of motion that are possible. It could be going down and to the left, it could be going straight down, or it could be going down and to the right. So if we only have one aperture, we actually get ambiguous motion because multiple things are possible when we only have one aperture. As we add additional apertures, we increase the likelihood of a greater consensus. So here is another motion detector, and again, you can kind of see it could go up and to the right, it could go to the right, or it could go down to the right. This aperture could go down and to the left, straight down, or down and to the right. This one could go up and to the right, or down to the right. And what you'll notice is the only one that all 4 of these apertures have in common is down and to the right. That is the only one that every single one of these codes for. As a result, because each of these 4 apertures codes for down and to the right, that is going to be assumed to be the match. That is the consensus, and that's why when you have 4 apertures, you are able to see the motion of the square as properly going down and to the right, compared to a single aperture where it really looks like it's going up and down, but there are actually several different motions. So additional apertures provide a greater opportunity for consensus and for context. Does that make sense? Okay. So where in the brain are these motion detectors going to be located? So we're going back to talking about magnocellular and parvocellular cells. Now, when we talked about color, we spent a lot of time talking about parvocellular cells in the lateral geniculate nucleus. Those are cone-driven circuits, and they are responsible for processing things like object details and color. But now we're going to talk about magnocellular cells. These are rod-driven circuits, So they're not color sensitive and they're not very detailed. They're designed to look at motion change over time. So we know that magnocellular layers in the lateral geniculate nucleus help create those first steps for motion processing. How do we know this? We know that lesions to those cells in the thalamus actually damage your ability to perceive large, rapidly moving objects. Now, here's our visual system. So here's primary visual cortex. If we are talking about motion, are we talking about a dorsal stream issue or are we talking about a ventral stream issue? Is it dorsal or ventral if we're talking about motion? Ventral is for object recognition. Would motion be helpful for object recognition? Maybe, and they do talk to each other, but remember that ventral is our what pathway? Dorsal is our where pathway, and figuring out where an object is involves object motion. So this is going to be in the dorsal stream of our visual pathway, and a critical area that we're going to be talking about is area MT. This is a middle temporal area. We call it MT, and we do actually find that MT is going to be really critical for motion processing. The majority of the neurons in MT are selective for motion in a preferred particular direction. It's always a good time for another root beer. Does anybody need some more time here? No? Okay. So moving on, we're going to look at this a little bit. So let's talk a little bit about the importance of MT. So these are still images, but we're actually going to try this ourselves as well. What you are looking at are called moving dot displays. And we're going to be looking at some different dot displays. So here, this is a dot display that has 100% correlation. What this means is that all the dots are moving in the same direction. We're going to look at some other displays that have 50% direction of motion. That means 50% of the dots are moving in the same direction. The other 50% are moving in random directions. And then finally, we're going to look at examples like these 20% moving dot displays, where only 20% of the dots here in purple are moving in the same direction, and the other 80% are moving in random directions. So Newsom and Pear back in 1988 actually looked at motion perception in monkeys while these monkeys were viewing these different random dot displays. Now, some of these monkeys had MT damaged. And what they ended up finding is that when they gave the monkeys that were lesioned these moving dot displays, they had much greater difficulty detecting the overall direction of motion in these dot displays. Now, some researchers have also found that when they electrically stimulate neurons in MT, they can actually bias motion detection. So if you stimulate certain cells in MT, you may be able to report seeing motion in static dot displays. So it might actually bias you towards seeing motion in certain directions. So to kind of give you a taste of what these monkeys went through, we're going to take a look at a few of these moving dot displays now. I told you we were going to be here a lot. Okay, so this is called correlated dot motion. So here, can you all tell me what direction all of these are kind of going in? Okay, can you say a word? Yep, that's exactly right. And do they all look like they're all moving in the same direction? Yeah, they're not all in the same place, but they're all moving in the same direction. So this is a case of what we call 100%. So this is when the dots are in correlated motion to the left. Now we're going to look at one that's 50%. Now this one's a little bit harder, is it? Can you all figure out the direction of motion in this one? It's going up. It's going up, but some of the other dots are moving in random directions. Now we're going to try this with 20%. I can actually see it. Can you? They're moving to the right. They're moving to the right, but it's kind of hard to tell because about 80% of them are moving in random directions. Now, if you want to have a better cue, here are the ones that are not moving in random directions. So I've removed all of those. You can see that they're moving to the right. So interestingly enough, this can be used as an indicator of motion sensitivity. It says that monkeys can normally detect the direction of motion when only 2 to 3% of the dots are moving in the same direction. So if you didn't have any problem with those 20% displays, odds are pretty good. We could probably bump that down to about 5%, and you might still be able to detect that motion. Following lesions to the region of the medial temporal lobe, MT, 20% or more of the dots had to be correlated for the monkeys to be able to detect the motion detection. So we would have to, this would be the best, like this would be the best the monkeys would be able to do. All right, that was kind of neat. Okay, so I want to talk a little bit about motion after effects. And for this, I'm going to have to go into a YouTube video. So I am going to pause sharing for this because I do not want to get copyrighted for this. So I'm going to go ahead and pause share and I'm going to pause the recording. So I'm going to go ahead and pause the recording. We're going to look at some research on motion after effect recording. Okay. So we're talking a little bit about motion after effects because we're talking about MT. MT has been shown to be a very critical area for motion detection in monkeys. And so, of course, you might be wondering, if we're talking about monkeys, is there a similar area that's critical for humans? Now, monkeys and humans are pretty similar. However, when we talk about brain-related things, they're not perfect analogs of each other. And what we actually find is based on research on motion after effects in humans, we do actually find that there are opponent processes for motion, much as there are opponent processes for color. And we find that for humans, this happens in areas like MT and also an area known as V5. Now, something that we didn't do that I would encourage you to do, we're not going to do the motion after effect again, but one of the things that researchers have actually found is that you can actually have what's called interocular transfer. So if you want to test this out, I would encourage you to do so. What you do is you do that motion after effect video that we did in class, like the one that we did earlier. Try that, but do it with only one eye open. Make sure that the other eye is closed and do it to completion. And then when it comes time for you to look around the room, change your eyes. So you were looking with this eye, now you're going to open this eye. And what you should find is that even though this eye was closed the entire time, you will actually get some motion after effect transfer to the other eye. It may not be as strong as the eye that you were watching with, but you will still experience a motion after effect. And that's because cells that are motion sensitive in areas like MT and V5 are binocular. That means that the motion after effect can transfer to an eye that wasn't even watching the motion. So we can get this really cool interocular transfer. So for those of you that are curious and you'd like to look at things like these, I would not recommend Natasha do it because watching that video was kind of hard, but try it tonight. See if you can get some interocular transfer going. You should be able to. And this basically means that motion after effects have to occur in cells that process information from both eyes. And it turns out that in humans, it's area MT that actually causes this to happen. Remember that primary visual cortex is the first part in the visual pathway where we actually start using information from both eyes. So it makes sense that areas like MT and V5 would also be binocular in scope. Does anybody need some more time here? Okay. So now we're going to do another one. We're going to do something called the waterfall illusion. How many of you like to look at waterfalls? Me too. So I'm going to have you look at a waterfall. Now, again, this is a YouTube video, so I'm going to go ahead and pause recording for this, but we'll talk about it after I resume the recording. So with the waterfall illusion, it's a very similar case of a motion after effect. If you didn't get that much of an effect with it, part of it was that it didn't take up too much of the screen also. That's a pretty dated video. You know how I know? Because the video was shot in vertical. And I know that that's not how you shoot phone videos. But if you watch that on your computer, you might have an easier time with it. I actually did see a little bit of that motion after effect with the waterfall. So even just the act of watching repetitive motion can produce a sense of motion when that thing becomes stationary. So the waterfall illusion is another example of a very well-known motion after effect. So it turns out that in addition to motion that involves positional change over time, we can also talk about two very different forms of motion. And so I've mentioned that we have positional motion, but we can also have what is called first order motion, and we can have what is called second order motion. So first order motion, this is a case where motion does not happen because of positional change, but rather we get changes in luminance. That basically means that brightness changes cause a sense of motion. Now, second order motion is going to be different. Motion in second order motion is defined by changes in texture or contrast, but not in terms of luminance. So whereas first order objects are defined by luminance, second order motion is defined by texture or contrast. And I'm going to give you a couple of different examples. Now, you might be kind of curious why we're not talking about what most motion is with positional motion. In a research lab, if you're wanting to look at motion, we're often going to be focusing more on first order motion and second order motion because those don't really have to change very much on a computer screen. So let's go ahead and take a look at an example of first order motion. And again, this is another instance where I'm showing a YouTube video. We have a lot of those today. So I'm going to go ahead and remove the pause the recording. Resume recording. We're going to go ahead and open that link. I'm going to have to enter in my password again, but that's okay. All right. Log in. Where's my login? Where is it? Wait. There it is. Okay. We're going to go to... Oh, it already remembers me. That's great. That makes it easier. All right. Chapter 8. Here we go. Okay. Different types of motion. So let's go ahead and take a look. So here is second order motion. So you can kind of see the stripes that are passing through here. Now, this is a case of second order motion. So in this case, that's what we were doing with that inversion. So basically what we are doing is we are inverting these sets of pixels over and over again. Now here's the same thing, but we just reverse the pixels. So this is how we're creating that second order motion. We start with this, and then we invert the pixels. So the only thing that actually changes in this image are the color of the pixels. Here's how they created it. They basically passed these moving bars that were multiplied by some stationary random dots. Almost all humans and other animals can perceive second order motion. And this is a case where we're not actually seeing true positional change over time, but we're still able to actually see motion. And that's pretty cool. And now I'm logged into that thing. Remind me not to log out again. Okay, so how do we use all of this visual information? Well, part of the reason that we need to know about motion is because not only are things moving around us all of the time, but you and I are constantly moving around all the time. Look at me, folks. I can't sit still. If I sit too long in that chair, I have to get up and start moving again. So you and I use motion to navigate the world and objects around us. So for those of you who have had me for cognitive psych, we talked about this a little bit, but for those who have not, I would like to introduce you to J.J. Gibson's theory of what he called direct perception. So J.J. Gibson originally developed his theory of direct perception based on research that he had done during World War II, looking at how people piloted planes. Obviously, this is going to be very important, and this kind of sets a really important background for his theory of perception. So around this time, you had a lot of people looking at things like object motion, object perception, and how we navigate those things because of the work that cognitive researchers did back in the 1940s, particularly with airplane pilots. And Gibson's theory of direct perception is basically the idea that you need to perceive objects, not just because they're pretty to look at or fun to look at, but you need to perceive objects because your goal is to interact with those objects. So direct perception doesn't really sound all that different from an idea called embodied cognition, that all of these different cognitive processes exist to help your body navigate the world and act upon objects and interact with other people. And so Gibson believed that when we are moving around in the world, we are using something called an optic array. And he defined an optic array as a pattern of light that falls on your retina. And this array has a structure and it contains all possible visual information from the environment. Now, at the time, in addition to a lot of work being done on airplane pilots, researchers were doing a lot of work with radio. And so because of that, Gibson believed that we kind of tune in, much as one tunes in with a radio, to the optic array to obtain visual perception. It's a little bit of a weird theory, but bear with me. We've only got 8 minutes left. So let's talk a little bit about optic arrays and optic flow. So what you're looking at here is an example of an optic array. So as you move through the environment, optic flow is going to happen. So basically, as you're kind of moving through the world, the position of points is going to change. So the position of objects is going to change as you move through the environment. So Gibson believed that basically what happens is that the area that you are walking towards has a central focus. Here you can see that that's marked as an FOE. FOE stands for the focus of expansion. So as I am walking in a certain direction, my center focus, kind of around where my nose is, that's where my focus of expansion is. As I move through the environment, information, like visual information, is going to radiate out from that focus of expansion. The farther away that something is from my field of view, the further out it is going to expand, and the more quickly it's going to expand. And additionally, new information is going to spread out from that focus of expansion. It's in the lungs. Look what y'all did to me. I need a cough drop when I get home. So here's another example. I kind of cribbed this from one of my old cognitive psychology textbooks. So this is another example of the optic flow field. In this case, in true J.J. Gibson fashion, we look like we're landing a plane. So in this case, the focus of expansion is right here in the center. It is going to stay motionless. And the rest of the visual field is going to move out and radiate out from that focus of expansion. The farther away that something is from the focus of expansion, the more quickly it appears to move. So if you want to have a little fun tonight and walk carefully when you do this, pay very close attention as you walk, pay attention to your focus of expansion and watch as new information moves in and out of your field of view. Maybe we don't do it while we're running, Michaela. Especially with how fast you're running for track. Like maybe you could get away with it with cross country running, but like with track running, don't do that. So here are a couple of other things that you need to know about optic flow. So remember that optic flow are changes in your optic array as you move through the environment. As I mentioned, distant information is going to exit the visual field, and new aspects of the visual field are going to appear from the focus of expansion, and they're going to radiate outward. And whenever you change your direction, there's going to be a shift in the focus of expansion. And optic flow can provide us with information about the direction in which we're going, the speed with which we're going, and our altitude. Remember, this is coming from research on airplane pilots, so one would think. Now, really quick, just to see if there's any additional information here. So here's optic flow. So here's kind of another example. So this is a display of random dots with a white pole. So image 2, let's see what happens when we move forward a very short distance here. So can you kind of see what happened here? So this is inward optic flow. Or that's outward optic flow. This is inward. So notice that in image 2, we're doing that focus of expansion where everything kind of radiates outward, meaning that we're heading towards something. Notice that when we're heading away from something, the focus of expansion radiates inward. So the focus of expansion kind of works and optic flow works in the opposite direction of what we're heading in. So if we're moving towards something, things are going to radiate outward. If we're moving away from something, everything's going to radiate inward. Okay, so I'm going to go ahead and stop here so I can hand back your exams. If you would like some extra credit, would anybody like some extra credit? Yeah, I figured y'all would want some extra credit. So if you want some extra credit, I'm thinking about doing something called an exam wrapper. Those who are in biopsych have heard me talk a little bit about an exam wrapper, just basically going through the questions that you missed and kind of making a comment as to why you missed them. Did you misread them? Did you get confused with your facts and things like that? And kind of just letting me know how you tried to study the material, how you tried to engage with the material, and what you're going to do differently next time, and some feedback for me so that I can help you with your learning as best I can. And so if I do that, you can get up to 10 extra credit points. Would y'all like me to do that? So I'll give you some directions on that on Thursday, and it'll be due next week. And remember, come ready to think about what day next week you would like to think about doing your data collection for your psychophysics project, either Tuesday or Thursday. Let me give you back your exams. Thank you so much, folks. Have a good day.